In this video, I want to talk about beta hat 1 and especially doing hypothesis tests for beta hat 1 in ordinary least squares OLS. So in previous assignments, we've talked about beta hat 1 and taking a sample of data and estimating beta 1 using a formula for beta 1 hat. So different samples will yield different beta 1 hats, which means beta 1 hat is a variable that cannot be predicted exactly, which makes it a random variable. Beta 1 hat is a random variable. Because it's a random variable, it has an expectation and it has a variance. The expectation of beta hat 1 and the variance of beta hat 1. The expectation of beta 1 hat is beta 1 under two assumptions. If 1, we are correct about our using a linear model, the data generating process is linear in variables. So I'll say a linear model is correct. And 2, the second assumption is that exogeneity has to hold. Exogeneity, which is defined as the conditional expectation of ui conditioned on big X is 0. And we're going to discuss that assumption, I think, in assignment 2.6. So that's the thing about the expectation of beta 1 hat. If we drew a picture of the probability distribution of beta 1 hat, it might look something like this. Here's beta 1 hat. And under these two assumptions, the distribution of beta 1 hat is centered on the true value of beta 1. That's how our explanatory variable x actually affects y. That's beta 1. What about the variance? The variance of beta 1 hat, that's the crucial thing to discuss doing hypothesis tests. So a hypothesis, well, I guess first, if the variance of beta 1 hat is very small, then it's saying that our estimate is very precise. Maybe it's something like this. It goes way up. That's a very small variance. And that's good for us because that says we're pretty confident in our estimate. We can estimate beta 1 hat precisely. But if we're estimating the variance of beta 1 hat to be very large, maybe something more like that, it's saying we're not very confident about our estimate. So here's how a hypothesis test will work for OLS. You're going to start with a null hypothesis that is H naught, which is that beta 1 is equal to 0. And that's saying that x does not affect y. HA, the alternative hypothesis, is that beta 1 is not equal to 0, which is saying that x does have some effect on y. Maybe it's negative, maybe it's positive, but it's unlikely that x has no effect on y. And then to conduct this hypothesis test, we're going to calculate how many standard errors away from 0 our estimate is. How many standard errors away from 0 our estimate is. And the standard error, by the way, how it's related to the variance of beta 1 hat, is that the standard error is something you get from the data. We're going to derive the formula for the standard error in the next video. But the standard error is the square root. It's like the standard deviation, but it's called the standard error because we estimate it. Standard error of the estimate of the variance of beta 1 hat. So you're going to get this from the regression output, just like the estimate for beta 1 hat. So the first step in your hypothesis test is to calculate how many standard errors away from 0 our estimate is. If we get an estimate of 3, and if we get a standard error of 1, The formula to find, and by the way, this is called the test statistic, or the t-stat. The t-stat is equal to beta 1 hat divided by the standard error for beta 1 hat. So in this case, if our estimate is 3 and we get 1 for the standard error, that would be equal to 3 divided by 1, which is 3, which says that our estimate of 3, given our standard error of 1, we're 3 standard errors away from 0. So that would be the t-stat in that example. And then finally, to finish up the hypothesis test, in a large sample, you're going to compare, compare the t-stat to 1.96. If the t-stat is greater than 1.96, then that means, in absolute value, then that means you can reject the null hypothesis at the 5% level. So if t-stat, the absolute value of t-stat, is greater than 1.96, we can reject the null at the 5% significance level.